Assalamualaikum everyone. This 130th episode is focused on calculating the EMF of an ideal source with negligible internal resistance. Two resistors in series to the source and a fully charged capacitor in parallel to one of the resistors. How do we analyze this circuit? You'll find it out, so just hang on, watch and learn. Here is the question. The EMF source shown in the circuit diagram has negligible internal resistance. The resistors and a capacitor are R sub 1 equal to 6.00 ohms, R sub 2 equal to 4.00 ohms, and the capacitor has a capacitance equal to 9.00 microfarad, and this capacitor is fully charged. So its charge capital Q is equal to 36.0 microcoulomb. The question is, calculate the electromotive force denoted by the Greek letter epsilon. Emphasizing the given data, we have R sub 1 equal to 6.00 ohm, R sub 2 equals 4.00 ohm, and the capacitance of the capacitor given as 9.00 microfarad. The charge stored in the capacitor is equal to 36.0 microcoulomb, and our target variable is the electromotive force epsilon. Since the capacitor is fully charged, when connected to the circuit, it neither charges up nor discharges. So the current in the circuit exists only through the two resistors, through the wire, and through the source. The current does not, or the charges does not flow to this part of the circuit where the capacitor is connected. In short, no current passes through the capacitor branch. Alright? Now, the capacitor is connected parallel to R1. Hence, the potential across R1 is equal to V sub C, which is the voltage across the capacitor. And this voltage across the capacitor is simply the amount of charge big Q that is stored in the capacitor divided by its given capacitance capital C. And since R1 and R2 are in fact connected in series, the current through each of them is the same. All right? And we emphasize that. All right? I sub 2 equals I sub 1, and each of this current is also equal to the total current, all right, generated by the source, all right, in this part of the circuit. Okay. We can find the voltage across R2 using Ohm's law. All right? Or that's actually the current through R1, okay, labeled I sub 1. So we simply divide the voltage drop across R1 by its given resistance R1. But in the same manner, using Ohm's law, we can determine the voltage across R2, all right, simply by multiplying the current I sub 2 by the given resistance of R2. And the moment we have the values for R, for V1 and for V2, all right, we can add them up because their total is just equal to the EMF of the source, epsilon, all right. So this EMF epsilon is just equal to the sum of V2 and V1. Moving on to our calculations, the potential across the capacitor denoted by V sub C is equal to the amount of charge, capital Q, divided by the capacitance, capital C, or 36.0 microcoulomb, which is 36.0 raised to the negative 6 coulomb, divided by 9.00 microfarad, or 9.00 raised to the negative 6 farad. And that gives us the value of the potential across the capacitor, equal to 4.00 volts. The potential across R1 is also equal to 4.00 volts because we said that the capacitor and resistor R1 are connected in parallel. So the voltage across each of them must be the same, 4.00 volts. All right? And applying Ohm's law, we find the current I sub 1. Okay? Which is simply equal to the amount of the potential across R1, V sub 1, divided by the given resistance of R sub 1, or 4.00 volts divided by 6.00 ohm. The amount of current I1 will be equal to 0.667 amperes in three significant figures. All right? And this same amount of current also passes through the second resistor R2. All right? So we emphasize that I sub 2 is also equal to 0.667 amperes, the fact that the two resistors are also connected in series. All right? And again, applying Ohm's law, we can now determine the voltage across R2. All right? So V sub 2 is just equal to the product of R2 and current I2. That is 4.00 ohms multiplied by 0.667 amperes. So we will get the potential across R2 equal to 2.67 volts. And finally, we can now calculate the source's EMF epsilon equals V sub 2 plus V sub 1, or 2.67 volts plus 4.00 volts. All right, so the EMF electromotive force of the source is equal to 6.67 volts. If the capacitor is removed from the circuit, the same EMF of the source and current in the circuit remain. The potentials across each of the resistors also remain the same. So that's about all. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.